Video we are going to discuss about sampling theorem and Nyquist criteria. This theorem actually is useful for analog to digital conversion, where we want to know uh, the rate at which we should sample our signal so that we are able to reconstruct the signal back. Suppose we have a continuous time signal xt, which means it has a value at every instant of time. Now let's convert, if we convert this signal into discrete time signal using a sampler. Sample has the values at different instant of time like t1, t2, t3, t4, t7 and so on. So this signal is called sampled signal. Now if these duration are t2 minus t1 equal to t4 minus t3 equal to 2, this means if those are sampled equally at equal duration, the distance between two sample or the time gap between two sample is same. So it means the signal is uniform sampled. So it can be written as T, 2T, 3T, 4T, 5T, 6T, 70 and so on. So this kind of a signal and can be represented as n x of nt, where n can be 0, 1, 2, 3, 4, 5, 6 and so on. So basically we have a continuous time signal and using the sampler we sample it uniformly and convert it to discrete time signal. Now before we going further, let's see why there is a need for sampling, why it is important, at which rate we should sample or how many sample we should take in a particular signal. Let's say we have some arbitrary, let's say sinusoidal input signal xt, and we want to sample it, and we sample it such a way that there are three samples for a one cycle for the positive cycle and three samples for the negative cycle. So basically six one cycle has six samples. So of course with this if we do the sampling with this rate, we can reconstruct our signal back as has been shown here with the envelope of with the blue color. So we can if we sample it such a that with such a rate we can reconstruct our signal back. Now if we decrease the sampling rate further, or we increase the space between the samples such that there are two samples only, one for positive and one for negative, and even then we should be able to reconstruct our original signal back. Now between two samples are large, so basically we are able to get a signal, but this signal is not our original signal. It is some different signal of lower frequency. This signal is called aliasing signal. So we see there should be a minimum rate that which we should sample so that we should be able to get our signal back. This is what Nyquist criteria is all about. It tell about what should be the minimum sample rate. Now to elaborate, let's assume that our sampling signal is xt and it has maximum frequency component in it, which is Vm, and it is band limited. This means the maximum component of the frequency is omega m, and its frequency dependent representation is omega w. We can estimate using Fourier transform. So in time domain it is xt, in frequency domain is x omega, and we are sampling it using an impulse train signal with the time duration between two sample period is ts, or frequency of sampling will be 1 upon fs, or frequency will be fs. Time domain signal representation is ct. So in time domain this impulse train signal can be represented as, or can be written as sigma summation n from minus infinity to infinity delta, which is equal to a function t minus n ts. So this is this time domain representation of impulse train function or sampler signal. Now for frequency domain signal, We know if we take its Fourier transform, we can get this frequency domain representation omega s summation minus n omega s summation n from minus infinity to infinity delta omega minus n omega s. So basically the Fourier transform of impulse train signal is also an impulse train signal in a frequency domain. Now we know that time domain multiplication of two signals is actually equivalent to division in frequency domain. Time domain, a sampler signal is Ct, its frequency domain is omega. Multiplication in time domain is actually convolution of those signals in frequency domain. So it can be written as 1 upon 2 pi x omega convoluting with the c omega 2s 2 pi x omega convolution, and then impulse train signal which was n equal to minus infinity to infinity delta omega minus n omega s, which can be rewritten as 1 upon ts summation n equal to minus infinity to infinity x omega convolution delta omega minus n omega s, and which it can be written as summation n equal to minus infinity to infinity x omega n x omega minus n omega is a signal x as the frequency domain representation was as a triangular pair with the maximum frequency of omega m, so minus omega m to plus omega m, and there are multiple of such that in both in negative direction and both and also in a positive direction. So if we see, so these triangles should not overlap, then only we will be able to get our signal back. If they are overlapping, then there will be loss of information. So for this, omega s minus omega n must be greater than omega n, which means omega s should be greater than 2m. Omega s minimum should be 2m. So these are the Nyquist criteria. This is the minimum that we should sample, and if it is omega s is lower than 2 omega n, then these two triangle will overlap and the frequency component will overlap, and we will no longer will be get able to our original signal back accurately. So what the Nyquist theorem is says that if we have a signal, let's say its maximum frequency component at present in the signal is omega m, then we have to sample those signal at least twice of the maximum frequency component that was there in input signal. Then only we will be able to get our original signal back from the sampled signal.